So, before telling that we are funded by Department of Energy, Division of Material Science and Engineering. So for that, I needed a microphone on, and we are grateful to our funders for allowing us to do all this exciting research. So here I'm going to tell you about our project, which we started almost 10 years ago, maybe slightly less, of looking at possible interactions, not possible, but at the interactions between magnetism and conduction electrons. Well, this doesn't seem to work. I think it's the same problem. Okay, fine. Right. So in the layer Dirac semimetals, the collaborators are on the screen here. There are two, Shao, who is our current postdoc, who is leading this work with me. She's of course a former postdoc who is now moved to Ames Lab, and here are Ames Lab collaborators. And of course, it's done in a neutron scattering group with John Requad and myself. Samples were made by Dirac, who was part of our group before he left about a year ago. We are getting excellent support from Brookhaven theory group, and of course, nothing of this would have been possible without our colleagues at Oak Ridge National Lab, where we do our neutron scattering work. All right, so the interest in Dirac semimetals, in magnetic Dirac semimetals, was basically arose from the fact that these are excellent metals, and they contain both very high mobility Dirac electrons in the. So the general formula is A manganese mainly, and here's the chalcogenide, bismuth, or antimony 2. And this is some either rare earth or alkali atoms, so Mn X2 systems, where X layers form a square lattice, which are sandwiched in between the M and X square lattice of manganese atoms. And so the first surprising observation, so these are very good metals, very low density metals. You can see quantum oscillations, at several kelvins to 10 kelvins temperature, indicative of light electrons, direct electrons with non-trivial Berry phase. At the same time, the magnetic layers carry very large ordered moments, which order, this is magnetic refinement of the magnetic structure, just to show that it's perfect. This is a heat capacity showing that it orders, the magnetic layers order at around room temperature in this particular material and carry a 4-4 magnet of magnetic moment. And still, at the same time, the Dirac layers do not scatter and show very high mobility, several thousand centimeters squared per second. So these are excellent systems to investigate whether one can manipulate Dirac electrons. Dirac systems are considered to be very promising for all sorts of electronic applications, starting with graphene, because low electronic densities are amenable to tuning. And here the idea is to see whether they are amenable to tuning with magnetic moments of the manganese ions. So, and the most widely considered tuning is converting a Dirac semimetal into a wild semimetal, where the spin degenerate Dirac cone is split into two wild cones, and that this can be done by the time reversal symmetry breaking, such as associated with homogeneous magnetic moment, which can arise from spin canceling in magnetic layers. So normally, the neutron scattering gives us structure which is collinear with magnetic moments along the c-axis in the interlayer direction. But if this would be slightly canted, then that could explain, or that could lead to splitting of a Dirac cone into two wild cones. And in fact, it was reported by from ARPA's measurement. So this is the ARPA's measurement of a Fermi surface actually, so the Dirac cones are here, they're strongly anisotropic, so this velocity is shallow and this velocity is high. So these Dirac cones in the measurement look almost like a nodal line, but actually these are 4 Dirac cones. This measurement, so these are cuts this way where velocity is strong, and they have somehow seen the splitting of these Dirac cones into what they postulated to be wild points. And then there was, so it was Zaliznyak and et al. Paper, and then there was a follow-up paper published in Nature Materials, by the way, where a group measured some bulk magnetization and claimed, yes, there is indeed canting. Now, canting, they claimed in Nature Materials paper, 0.018 degrees. We were talking moire, we were talking point 0.02 of a degree. Can you imagine a bulk crystal with something that's defined to 0.018 degree? And then, of course, in order to have an effect on an electronic structure, I mean, can you believe that 0.018 degree canting of magnetic moment, even manganese or 4-bore magneton, can lead to some serious changes in the electronic structure? And of course, it's unverifiable by Newton scattering because, we can measure a few degrees, but we cannot measure 0.02 degrees. And of course, this is bulk measurement. So it is, I mean, you have all sorts of little ferromagnetic mixtures. And so you measure it and you say, okay, you assign it to a thin can. So it's not serious. However, soon afterwards, the wild splitting was postulated in a similar, in a system material, calcium manganese bismuth 2. So we replace ytterbium with calcium. Again, quantum oscillations, tens of Kelvin, high mobility, low electron mass. So here is Shubnikov, here is de Haas-Mann-Alphen, here is Shubnikov-de Haas. You see all sorts of quantum oscillations. Very similar structure with bismuth layers and intervening manganese layers ordered with, again, very similar magnetic moment about 4-bore magnetons. DFT calculations do show you the Dirac cones here. And then this is a busy slide, but I walk you through. So this is a resistivity measurement at the constant temperature. Here the resistivity shows some kink at around 50 Kelvin. You see something, you want to see wild point or, wild system. You say, yeah, that's of course, that's what it is, wild. And then again, the optical conductivity also showed some anomaly at the same temperature, indicative of Fermi surface reconstruction. Okay, fine, certainly wild. And of course, that's because of spin canting, because that's what you see what you are looking for as often. And so again, they did several bulk measurements here, torque magnetometry. Fortunately for us, the prediction was from the torque magnetometry that the canting is about 10 degrees. Now, 10 degrees is a credible canting. You do DFT calculations, and you indeed see substantial, measurable and consequential Fermi surface reconstruction. But we can detect 10 degrees in neutron scattering measurement because appearance of a homogeneous magnetic moment on top of lattice would mean that the lattice Bragg peak would have to increase at the temperature where the ferromagnetic moment arises. And so the calculated increase for this weak lattice Bragg peak that we have measured for 10 degrees would be like that, and that's nothing that we see. So there is no canting. This here is an order parameter that we measure. The magnetic order appears at around 270 Kelvin, and there is nothing in the order parameter indicative corresponding to this anomaly at 50 Kelvin. This susceptibility basically consistent with the order parameter showing the antiferromagnetism. All right. So what's happening at the temperature? Well, what's happening at the temperature is that we observe the superlattice peak, first in an unpolarized Newton diffraction. This is superlattice peak corresponding to doubling of the unit cell in C direction, so doubling of the layering. That peak has both magnetic and non-magnetic components. It is also seen in X-ray diffraction, of course, because it has a lattice contribution. But in addition to the doubling of the unit cell, X-ray diffraction also shows that there is an orthorhombic distortion in the plane. So there is a structural transition at this temperature. What is that structural transition? Well, we have measured the limited set of Bragg peaks, but we were able to do some limited refinement. And what we realized is that what's happening is that the square lattice originally of this calcium manganese bismuth 2 high temperature square lattice of bismuth, which carries the Dirac electrons, actually disproportionates in forming these zigzag chains. So in the past, we called it bond order wave. In fact, from our limited refinement, we weren't able to uniquely determine whether these zigzag chains form in manganese layers or in bismuth layers. However, from the absence of magnetic response at that temperature, but from the presence of resistive response, we inclined in favor of antimony zigzags, bismuth zigzags. And then, I mean, this paper is still being finalized. When paper was almost completed, in fact, somebody pointed my attention to an old paper by these authors, a very difficult chemistry paper. I mean, it was pain to read it. It has all sorts of things thrown in, where authors basically explain that these materials, and they focus on antimonides, but also show the bismuth version. At the time the paper was written in 1887, they knew that strontium zinc antimonide does show this zigzag chain formation, and they assigned it to a two-dimensional piles distortion. So I gave up reading this paper 2 times before I finally finished it, after looking up who this Hoffman is. It turns out, yeah, it turns out he is Nobel Prize winner in chemistry. And then I realized, yes, that's exactly what we observe. So they predicted it, and now actually most of these materials, at the time they predicted it, only one material was known to them to show this zigzag distortion, which is the Piles transition in 2 dimensions, and it was believed to crystallize in that phase. Now what we see here is what we have shown, that calcium manganese diantimonide actually undergoes a distortion at around 50 Kelvin. Now, another material that was also recently reported to have the same distortion is ytterbium manganese diantimonide, and it's an Uwatoko group measurements. So they shown the neutron diffraction evidence for the distortion. It's again very similar formation of zigzag chains here in the antimony layer. This time not in the bismuth layer. And there is a Fermi surface construction where one Dirac cone remains, but the other one in the perpendicular direction goes away. So it is a Piles distortion. Of course, at this time, it was these authors believed, like Hoffman way back, that material just crystallizes in this phase. We actually measured the temperature dependence. So here are diffraction data, and this is the temperature dependence data for a regular Bragg peak. So the scale is like 1.1, so it's basically constant. And here is the temperature dependence of the superlattice Bragg peak. And so what we see here is, again, that this distortion actually appears at around 800 Kelvin. So this is another example where we see this Piles transition emerging in Dirac electrons emerging at a finite temperature. So the material doesn't crystallize with it. All right, so another, slightly switching gears, another way to, so here we didn't find the evidence for interaction between magnetism and Dirac electrons. What we found is the interplay between structure and Dirac electrons, the emergence of the Piles transition in the Dirac electron layer, which has been predicted by Hoffman 30 years ago or more. Now, we are after detecting the interaction between spin layer and the Dirac electrons in the convection layer. So one way to look for it is to measure the spin wave dumping of the spin waves, and we did that in ytterbium manganese bismuth 2 and ytterbium manganese diantimonide. And we were able to refine a very tiny, I mean, this is still, I'm still not 100% convinced that it's at the edge of what we can do in neutron scattering with this sort of energy scales. So the tiny damping in the ytterbium-manganese bismuth 2 and the interlayer coupling, of course, is another evidence that the magnetic moments are coupled to conducting layers, because there is no way coupling between magnetic layers comes, it has to shoot through the conduction layer. So there is no way it doesn't involve direct electrons in the conduction layer. So as this damping increases from bismuth material to antimony material, the interlayer coupling also increases. So this seems to be consistent, the increase of coupling between the magnetic layer, between magnetic moments and direct electrons as you go from ytterbium-manganese bismuth to ytterbium-manganese diantimony. Okay. We also understand theoretically the reason that the damping is so small, and that is because there is very few of these Dirac electrons. The density of states in the Dirac cone is very weak. So we can, our theorists were able to put together a simple model of Dirac electrons coupled with spin waves coupling. And the coupling constant, with a very large coupling constant, we actually can explain very small damping. So again, the coupling is strong, but the density of direct electrons is weak. So in fact, what this implies is that if you would indeed be able to create this canting, we would actually have substantial influence on direct electrons. We would create wild points. We haven't found a material with that canting yet. Now, of course, the simple way to quantify the interaction is as a function of material composition, is to just measure the interlayer coupling as varying material compositions. This has been done also by Oxford group. So this is Andy Buttery's group measurement in strontium-manganese bismuth 2 and calcium-manganese bismuth 2. And what they have shown is that switching from strontium to calcium, the interlayer coupling switches from antiferromagnetic to ferromagnetic. And you can see that by measuring the interlayer dispersion. So this is a dispersion of spin waves, and the dispersion in the interlayer direction is not very well seen here. So this is another view of the dispersion in the interlayer direction in strontium-manganese bismuth 2 and calcium-manganese bismuth 2. So the dispersion in the interlayer direction is very weak. The coupling is small. The in-plane coupling is strong. So dispersion in the plane, it's very steep. But this dispersion in between the planes is weak. However, the bandwidth of this interplane dispersion determines the and its position of its minima. So for antiferromagnetic coupling, the position of the minima are at antiferromagnetic positions. Here it's 1 minus 1, and for ferromagnetic it's at 0, and so on. Okay, so we set up to measure a similar compositional dependence in the antimonide series, but our samples were too small. I mean, usually, if you want to do a compositional work, you don't have big samples that neutron scattering Newton scattering spectroscopic measurements require. So traditionally, a spectroscopic measurement requires like gram plus samples. Cheddar made us like 100, 200 milligrams at best samples with different compositions of calcium, strontium, manganese, bismuth 2. And so we were stuck. So the end material has been measured by Ames group. They have refined the interlayer coupling to be ferromagnetic. But our work was stuck here. So I'll do the intermediate conclusion. What I've shown so far is that the lattice symmetry, which determines which is the origin of Dirac electronic bands, is not necessarily what materials crystallize with. I mean, you can have this Piles distortion with changes. This challenges DFT predictions, of course, because you have to compute. You do a DFT calculation for ytterbium-manganese diantimonide, but whether you calculate it in the high temperature phase or in the low temperature phase, you will have different results. So we observed the Piles charge density wave, and the spin fermion coupling from the spin wave damping is weak. So, but the coupling constant itself is strong, so the effect of magnetism on the conduction electrons would be strong if we would be able to find a material with this weak ferromagnetism. Okay, we were stuck by trying to measure spin waves on these small samples. We decided to measure diffraction and to just study magnetic structure. And surprisingly, we were able to measure spin waves on a diffractometer. So this is the second part of this work, which is an experimental one, where we have reinvented actually an old method. However, using these new updated instruments at Oak Ridge National Lab, one can one can perform measurements on a diffractometer that were unimaginable before. So what diffractometer or diffraction measurement does, it takes a neutron beam with a given energy and then measures all scattered energies are collected by detectors in a given direction. Now, if a detector is now a large position sensitive detector, it integrates in this length of the scattered wave vector for all different directions. So a single integration corresponds to integrating wave vector in the wave vector transfer to sample, which depends on the energy transfer to sample, right? So normally in diffraction, only elastic processes are considered. However, all processes are being picked up by detector. So what we measure, or what we can see in our measurement, is the integration. And so this is the measurement, which shows, this nice, interesting signal measured at different temperatures from a 200 milligram sample. Each measurement was like 3 or 4 hours. It is a spin wave spectrum. And here is simulation of this spin wave spectrum. So what we have discovered is that we can measure a refinable spin wave spectrum, which allows us to determine all 4 Hamiltonian parameters on a very small sample in a very short time. The interlayer dispersion is picked up by measurements at different positions vertically on the detector, and you can see it by your hand. You can see it by a naked eye as this distance from the Bragg peak. Here is a Bragg peak, magnetic Bragg peak, and the distance of the beginning of this dispersion from magnetic Bragg peak determines the gap, energy gap in the spin wave spectrum. So because this is a projection of a spin wave spectrum along this trajectory, it's just energy momentum conservation. All right, so we can easily fit this to a one-dimensionally projected spin wave and refine all the parameters of the Hamiltonian. Actually, as I say, in 2 days, it was an accidental measurement. We just had a weekend where we weren't able to change the sample, and so we carefully measured this sample, and we were able to measure temperature dependence of the spin gap. Here is the spin gap at many temperatures. This is the order parameter. Spin gap sort of tracks the order parameter. The in-plane couplings, which are temperature independent, as you expect, and the effective interplane coupling, which actually it's effective because it determines the ordered spin wave. So anyway, what we obtained is a very complete characterization of our sample in a diffraction measurement. When I showed these data about a year ago at a meeting where my friend Professor Takasato from Tohoku University was present, he was excited. And I suggested that, in fact, a diffractometer measures the given incident energy, but you can actually measure it at several different incident energies. And then you will basically have a spectroscopically resolved measurement on a diffractometer. Why this is, this is an advance in our field is because covering a large array of scattering angles with energy analyzing machine, like analyzer, crystal analyzer, is very difficult. Or you can go to time of flight, and then you have to, on a reactor source, you have to chop your beam. But this method doesn't require that. And then if you measure at several different incident energies, then you can actually, you obtain an intensity that it's a linear function of you sum over energy transfer over the scattered energy, but it's basically some linear matrix multiplication of your scattering function and your energy conservation transfer function, and you can actually invert it. So this gives rise to a new technique. When you measure several incident energies, then you collect all the data and then you invert them, and you can obtain the original scattering function. So he made this example of this is a calculation example of a ferromagnetic spin wave, which should look like that. And then if you do several steps in EI, you would obtain the diffuse intensity on your detector, which would look like that. And then you invert it back, and you obtain your spin wave. Of course, this inversion is imperfect because the coverage of your phase space is uneven. And but the technique is extremely powerful. Now we can do neutron spectroscopy on tiny samples in a reasonable amount of time using a diffractometer at a reactor source. And in order to do this type of measurement intelligently, here is where machine learning comes. It's a very difficult optimization problem because you need for every incident energy optimize where you position your detector, how you rotate your sample in order to even out the coverage of your phase space. But this can be done, I believe. It might, this difficult optimization problem perhaps can be solved by using AI and machine learning. This is my second part of conclusions. We have reinvented this diffraction method where we can measure spin waves on a modern diffractometer. And this measurement provides a very efficient tool for screening quantum materials because, and again, this is amenable to a machine learning AI guided measurement where you have your small samples, you can just put them on a diffractometer one by one and then rotate them intelligently, screen them, and then refine the interaction parameter. It gives 1 to 2 orders of magnitude increase in throughput, which allows us to study much smaller crystals than typically studied by neutron spectroscopy. So that's it. Way too fast?
No, perfect timing.
First is that you mentioned that the Paris distortion was concerned in the antimony compound.
Yeah.
Right. But what about the bismuth, the ytterbium bismuth and the calcium bismuth?
Okay, so right, so the ytterbium manganese bismuth does not have this distortion.
Ytterbium does not.
Ytterbium manganese bismuth does not show this distortion. So calcium manganese bismuth, as I have shown, only has this distortion appearing at 60 Kelvin.
Above or below?
Below. So it is a low temperature phase. So, as you cool it down, you have a lowering of your symmetry. You have this spiral transition or charge density wave, if you like, with these zigzag chains emerging at below like 45 Kelvin, right? Now, in ytterbium manganese diantimonide, the T star, the spiral transition is roughly 800 Kelvin.
Okay.
Ytterbium manganese Sb2. In ytterbium manganese bismuth 2, it's probably below 0. So, I mean, it doesn't happen. What I show, the temperature of the distortion is material dependent. And there are materials like ytterbium manganese bismuth 2, which do not show this distortion down to 1.5 Kelvin.
Okay. My second question is that you claim that the Paris charge density wave.
Yeah.
Do you see the peaks in X-ray diffraction related with charge density wave?
Yeah, that's, I mean, not only in X-ray, in neutrons and X-ray, yes, that's, I mean, you see, because this charge density wave does not increase the unit cell in the intralayer direction. In the layer, this formation of zigzags do not change the unit cell, right?
Right.
It's just this proportion action within the unit cell. But the stacking, because of this zigzag, it increases stacking by factor 2. And so this is the Bragg peak 308.5 observed by X-ray diffraction, which corresponds to that increase in stacking length in that spread. But in addition to that, X-ray diffraction also shows you, so this is a strain, you see the Bragg peak, the in plane Bragg peak, H08. So this is an in-plane Bragg peak. It shows splitting. You see, this is high temperature, single nice peak, 9 Kelvin. You see there is a splitting of this peak, which means that A and B lattice parameters become unequal. So there is an orthorhombic distortion in plane. So there are two evidences in this X-ray diffraction for this orthorhombic zigzag distortion.
Did anyone get in to measure VC peaks?
No, I don't think so.
This David.
Yes, what is the carrier density? And I thought on one of your slides, you said there was strong interaction with the electron, between the electrons and the magnetic moments.
I don't think I have carrier density. Yes, so the strong interaction, when I say that's a theoretically derived quantity. So
I'm just wondering whether the high mobility is a mystery or whether it makes perfect sense.
I don't know. Yeah, but carrier density is low. I think it's 10 to 15 or something.
Oh, that low. Okay,
I have to look it up. But yeah, it's not like graphene, but it's
okay. Low, I was thinking more like 10 to the 20. Okay, still pretty low for a metal.
maybe you're right. I have to check it out. I remember it's low, but
Okay.
low for a metal. Maybe I have to check.
Any other questions? So Igor, I mean, I guess things like automation are becoming important if you're going to run through many samples, and both in the growth and then ongoing through multiple samples and multiple temperatures. Did you think about it?
Yes,
What that means or what would be necessary?
the first step would be an automation that would design the measurement. That we haven't done that, but
I mean, could you combine this with powder in elastic, where you're doing a lot of screening through as well, where that's fast too.
right. Powder-
The whole piece is better than some other.
You can combine it with powder and elastic. This is not full replacement for powder and elastic.
No, I mean, just using both of them together, you know, the initial screen through with powder and elastic, getting or whatever,
Yeah,
and then it's all automated when it's going on to the
Yes.
action method.
yeah, exactly. Right, all right. Yes, you can, of course. This sort of a second iteration for a measurement where you would get a better handle on dispersions.
You've got to do the temperature changes and so on with lots of different samples too, and then that's where it becomes complicated. It's just you got to change samples, change temperatures, all the rest of it.
Yeah.
You could, you know, you've got lots of AI methods that are good at working decisions for changes for the actual mechanics of automation.
Well, it's all matter of funding. If we have people to put onto it.
Yeah, and it's not necessarily expensive. I don't think it's crazy expensive to do something.
Yeah, it's just a matter of someone doing it.
Yeah.
So. On the scale of LDRD at Oak Ridge or something,
Yes.
but we are not at Oak Ridge.
No. But we're making recommendations at the moment.
Yeah, well, this is a way to go for screening quantum materials, you know, to optimize the experimental procedure.